were talking about, or I'm sorry, last week, Thursday, we were talking about this motor control current, motor control circuit, and the motor control circuit powers the magnetic starter. It can either come from the power supply with the motor. Just your power comes into the relay L1. You pick up L1 and you take it out to your stop-start switches, and you bring it back to your relay. Okay, that's one way of getting power. The other way of getting power is bringing a separate circuit in. So you have, like I have a motor control center that has, 40, 50 motors that are controlled out of that motor control center. So I bring a circuit in and I tie it in. So I come off the panel. The panel might be on the motor control, or it might be elsewhere somewhere within that motor control center. Carries lower signal current to direct function of controller. Okay, so when we get power, they're usually rated 120 volts or less. When we get power off the motor control, we go off and we control the circuit. That circuit, all it's doing is that these have lights, that's whatever these lights use, and whatever this coil uses. So that's the only power that's going to be. There's no load. The load-wise, this is it. Most transformers, when you have, let's say, 480 coming in, and you're knocking down the voltage to 120 volts, and you set a transformer, you're going to have a primary protection, you're going to have a secondary protection on the transformer. I got the ones in the classroom. I don't have one with me here, but I have in the classroom. And you've seen those before. I passed them around when we did motor controls and electrician too. And so it has overcurrent protection on both sides. Okay, those transformers were only a 50-watt transformers. That's it. Doesn't have to carry a lot. Or they're in this coil to open and close. And if these have lights, whatever these lights are, the wattage of the lights, that's the only control. That's the only current that would be running through the control circuit. So you can put a lot of controllers on one circuit. Why? Because there's a very small current. Oops, wrong way. Okay, control circuit, Article 100. A circuit of control apparatus or system that carries electrical signal directing the performance of a controller, but not main power current. So that's what I was talking about. It's only carrying the current of the controller. Control circuit protection. It says additional protection. Well, let me go before I get to that. The motor current does not carry a high current used to run the motor. The motor control circuit only carries a lower signal current used to direct and function of the controller. In most cases, the controller is rated at 120 volts or less. A control transformer is used to reduce the voltage of a high voltage supply. Okay, that was part of the other one. So they usually use the transformer to control the circuit. Circuit protection, additional protection for conductors tapped from the motor power on the load side of a protective device. So if you have a motor, I have a circuit, comes off, let me see. So here's my power. So this one is a 240 volt control circuit. So here's my power, here's off one, this is L1, L2, L3. Here's my contacts, and here's my overloads. So they're getting power off of one to come to the coil. This is the coil. And they're getting power off of another one. So this is L2. So this is going to be a 208 or 220, 230, 240 volt coil. So they're getting two. Okay, so in that case, you don't have to have protection. They usually don't do it if it's at 120 volts. But because more likely your breakers, your short circuit protection should be able to handle it. But if you're coming off of here and you're going to the transformer, then yes, you have to protect it while you're changing the voltage. So now it has to be protected. So you have to have a transformer. In the back room I have one that's 120 volts, and I have another transformer that is 30 volts. So you're protecting this wire. Let me go back. Okay, so it says control circuit conductors must have overcurrent protection. When the control circuit becomes overloaded and opens, the circuit must also open. So in case we overload that circuit protection, it overloads, it opens up, and it opens everything else up. So obviously something else may be tied into something. The conductors are tapped from the motor conductor on the load side of the protective device. The control circuit conductor must have a supplemental protection. The maximum rating of the control circuit overcurrent protection device is based on the conductor size. These values are listed on table 430.72b of the code. Control circuit conductors can also be supplied by a separate source, such as service equipment or power panel. In this case, the circuit is considered a remote control circuit, and the overcurrent protection is based on the conductor ampacity. Section 725.43 specifies that the conductor and capacity derate factors of section 315 are not considered. So what does that mean? Is if I got a wire going through a hot area, I don't have to derate the wire. Why? Because it's not going to be carrying a lot of current. Again, if it's coming off a transformer within the motor control, they're talking about 50 watts. So there's not really a lot of load on it, so that's why we don't have to derate the conductors per control circuit. Remote control circuit protection based on the conductor ampacity. So if I got a 14 gauge wire going across, I got a 15 amp breaker. I got a 12 gauge wire going across, I got a 20 amp breaker. And you size it accordingly. You can use for controlling, remember, smallest building wire is a 14, but for controlling things, we can use the smaller wires. Why? Because it's only carrying minimal currents. So limitations on small conductors, number 18, 7 amps, and number 16, 10 amps. Separate disconnect service can be used for the motor power supply and the control circuit. However, the devices must be adjacent to one another. So if you're going to use, you have to be able to turn off. A lot of times what we do is, let me get back to this drawing. When we come off these drawings, we'll come off of here, we'll go to a transformer. Let's say we got 480 coming in, or even 208 or 230, 240 I got coming in, and I'm getting 200, I'm getting 2 hots because there's no neutral. Motor doesn't need a neutral unless it's 120 volts. A motor does not need a neutral unless it's 120 volts. For most parts, a single-phase motor's got 2 hots. A 3-phase motor's got 3 hots. No neutral. You don't see a neutral anywhere on there. So we can come off of this, okay, with our 2 hots, go to the transformer, put a primary side transformer, put a secondary side transformer put a primary side fuse, put a secondary side fuse. Now we can knock it down to 120 volts, 115 volts. Knock it down to 36, 48, 24, whatever voltage you need, you're applying. That's all you need, okay? Because they do make them in 36. We have that one in the, we have that one motor starter at the class, and that's a 36 volt coil. Okay, for most parts 120. I do have the one starter that's a 220 volt coil. In this case, I wouldn't need to put a transformer. If my applied voltage is 240 volts, I can use a coil that's already inside of it. Okay, remote control circuit, Article 100. Any electrical current that controls any other circuit through a relay or equivalent device. So now it's just a circuit that comes in that helps control something. It's not carrying current. I mean, it's carrying small currents, but it's not carrying current of the actual load, which would be the motor. Motor controlled connections. The wire diagram is used to show the connections and components of a motor circuit. The wire diagram shows a control circuit. Oops. Forgot to go forward. I'm back. New button thing, so can't figure out where the buttons are. So in the wire diagram, our thin lines, which is these blue ones, is our control circuit. The thick lines is the motor power. So here's my power coming in, power coming in, power coming in. Okay, so this is my L1, L2, L3 contacts, my overloads, and then coming off the overloads would be T1, T2, T3 going to the motor. Okay, this is a 3-wire control. This one here is a 2-wire control. Okay, so you only have one way to turn it on. Okay, so whatever this closes, it turns everything on. The only problem is that one stays on, power goes off, and we'll get into that a little bit. Oh, I'm sorry. Yeah. This is a wiring diagram for the motor control circuit and the power circuit. And the other one here is an elementary drawing of a circuit shown. This is a 2-wire control circuit. Those are my 2 wires. So this may be a switch. When I turn that switch on, this closes this up and the motor starts working. Okay, we're going to be talking about 2 wires in a bit. I'm going to be talking about it in a bit. But now that I have the diagram up here, I can tell you a little bit. Okay, with this one, because the power is coming off, once the switch is closed, it goes into the coil. Because I have contacts somewhere. I have an overload relay contacts, so I have a contact somewhere. So what happens is, well, this one doesn't show. This one's a single pole switch. I'll get to that back in a bit. Okay, with this one, I close this switch, this motor starts working. Same thing with this one. This is a 2-wire. Same thing with this one. It's the same one. The same one. It's an elementary drawing. Here's the actual, So I close this. I close this switch. Power goes to here. Guess what? This goes to this contact. This contact is always closed. Comes back to the coil. The coil. This one would be hot here all the time. This is just waiting for it's hot. I close that switch. That gets hot. This motor comes on. Okay. The only problem with this is power goes off, and that switch is in the on position or the closed position. Okay. What's going to happen? That motor's going to come right back on. So you have to be careful with that. Okay, this is the elementary drawing, and that is a wiring diagram. And then this is the elementary drawing of a 2-wire. Always remember is your darker lines would be your power for the motor, and your thin lines would be for the control circuit. Control circuit are always specific. So the control diagram shows the circuit in the off condition. Okay, so what is it here? Anytime you look at the drawing, it's always in the off position. It's always in the off position. Here's the off position. I was talking about a 3-wire. I'll talk about 3 wires tomorrow. Today we're only going to stay with these 2 wires, so I got these diagrams on me, in front of me. Okay, so again, this is a 2-wire. You have to be very careful. It says contact show refer to normally open, while will close when energized. These contacts shown closed in the diagram will open when the certain energized and are called normally closed. Overload relays can open or close depending on whether they are associated relay are open or closed. The control circuit is the most basic form without a power circuit. Is illustrated by figure 14.6. 3 components of the starter. Okay, so again, to this wire diagram, how does this work? This is a 2-wire switch. The switch is always showed in the off position. Okay, so there it is off because the switch is open. Once the switch closes, provides power to here, motor comes on, motor works. This motor will not close. These contacts always shows them in an open position. Okay, here's a closed contact. So this is what a closed contact looks like. It's got that line going across. So if these were in the closed position, these would have a line going across. Okay, this one's closed. These are open. Okay, that here is my switch here. The coil, and then this would be that other one. Okay, this one goes through the overloads. So this would come down to my overloads. I have my normally open and my normally closed, whichever one I want. It says NO. It says NO, and I've got 2 screws and NC. Normally closed, normally open. So what it does, it comes off the coil and it comes to here. If I want it normally closed, I will tie into the 96 and 95. Okay, so I come into here. From here I go out that way. So this is always closed. So when you hit the switch, right part of here goes out. What does this do? Is if this overheats, this is your overload protection. This is what's protecting the motor. So this is sensing that current. All it's doing is sensing heater. That's what we call them heaters. The overloads, that's what we call them heaters. They're sensing that heat, the current. They're not reading current, they're sensing that heat. As that heat gets up, if there's a problem, if the motor's running too hard because you haven't oiled the bearings in 6 months to a year, you haven't changed the belt, and the belt's starting to tighten up, or whatever it may be, or you got the belt too tight, and it works the motor starts to get hot. Well, that heat goes on the wire comes to here, this trips out. It's got this little red button. If this trips out, if you're hitting the stop start and it doesn't come on, more likely this tripped out. What you have to do is come over here, hit that red button, push it down. Now you can reset the overloads. Okay, you reset the overloads. I just stuck them in there, didn't have them tight. All right. Motor control connections. A control circuit diagram shows the circuit as an off. That's what I was talking about. So normally open, closes when the energized. Normally close, it opens when energized. So again, so say if I wanted it, this one is normally open. This one is considered normally open because the switch is always open. So it doesn't work until I close it. Okay. Now when I have it at normally closed, this switch would be on, but when I open the switch, it comes on. So it works the reverse. So let's say I have two motors, and motor A is running for 12 hours, and then motor B starts running for 12 hours. So one is normally open and one is normally closed. Okay, well, when the contactor comes in and it changes, and when it gets to a certain time, the time clock is telling this one, okay, you come on. And it closes the other one. So they're turning on, off and on at different times. Okay, you connect them a little different, but one is okay. So normally closed, when open, energized. So again, this power may be sensing from somewhere else, and it keeps it open. And you have it that way, so let's say you have two motors on a circuit, they both don't run at the same time. Okay, so one is always off, one is always on. So when you turn the switch on and it gets energized, the switch opens and turns that one off, and it turns this one on. And here's showing the switch. Okay, this is another circuit diagram. They called it a schematic. I'm sorry, forgot to mention this. Okay, so this is a wiring diagram. These are wiring diagrams. These are wiring diagrams. These are our wiring diagrams. This is our schematic or a ladder. So you have the wiring diagrams and then you have the ladder. So here's one hot, here's my other hot. I constantly do this on the board when I show my receptacles parallel circuit for how we wire. Why do we wire the way we wire using parallels instead of thinking? I put in the single poles and I put in the three ways and I put in all the receptacles and I make my ladder. So I have my hot and I have my neutral. So I show you a ladder diagram. Okay, this is a ladder diagram. Pilot devices. Switch that operates control circuits, single pole and double pole switches. So when you have a circuit, you can have on and off switch. You can have a motor controller. Still has on and off. There's my off, there's my on. Okay, these allow you to get it right. That there is off. Now you see how it has this groove. Now I can get a padlock, lock it out so nobody can turn it on. Okay, so that's what this helps compared to a switch. This one does have a means so you can lock it out. They do make a lockout for switches. This one makes it easy. Two varieties of switches are available: single pole switches and double pole switches. They also make a 3-pole. That was at the beginning of the chapter. They had a picture on that on figure 14.1, page 202. So they do have them. So they both, it says circuit completed when the switch is closed. So when you switch is turned to the on position, the switch closes and it comes on. They also have various types of pilot devices. You have a float switch, a limit switch, a snap switch, a foot switch, and a pressure switch. What is a float switch? Okay, a float switch is like that bobble thing in your toilet. Okay, when you flush it, it lets all the water out and it comes out. Once it fills up to a certain point, it turns off the water. That's what a float switch does. So it either works on when the pressure gets low, it comes on, or when the pressure gets too high, it comes on, saying, you know what, I don't want more water than this. So you're controlling the water. So it can either turn the water off or turn the water on. Say the water's getting up too high, you want that switch turned on, hey, start pumping some water out. You know, like a pump. You got a water pump. It has a float on it. Well, once the float gets to a certain height, your pump comes on. Okay? So you don't want it to overflow, that's why the pump comes on. Well, in your toilet, it's the opposite. Once it gets to a certain level, it stops, and you can do both. And this is a limit switch. A limit switch is, I have that little one that I showed in the classroom. I didn't grab a lot of these things. I should have, but I didn't. I don't want to have to bring the majority of the shop with me and then have to haul it back again. But the limit switch, how does it work? Okay, so a limit switch, you have a conveyor belt and it's moving, and you want it to stop at a certain point. You know, so I'm working, assembling something, and I got 3 minutes to assemble it. So the limit switch moves over, hits the limit switch, and it goes to a timer relay, and it sets a relay. So all of a sudden, okay, turn on. But this relay, you got it set at 3 minutes, so all of a sudden it goes till it gets to 3 minutes. Once it gets 3 minutes, now it moves again till it gets the next bump on the conveyor belt, and it hits that limit switch and it stops. So the limits, it allows something to move. The limit, it only limits it. So that's one way. The other reason, the other times you use a limit switch is you got something like your garage door. It comes down. You know, the garage door has a little eyes if somebody walks in and it shuts it off to stop it, or when it comes down it knows when to stop. Okay, so there's a limit device that allows only so much cable to come out. All that is set, preset. Once it gets to a certain point, it stops. We had them on the boat docks down at Marina del Rey. You know, so when the crew went out there to practice rowing, they had the switches, and it had 2 limit switches on both sides, and they had little balls. Once so much cable came out, there was something that hit, and it turned the limit switch off. Okay, we always have to go back, we always had trouble because the little crabs get in there and they get stuck under the limit switch, and the switches wouldn't go off. All of a sudden, you know, one stops and they're like that. But that's what the limit switches do. It only allows so much, and then when they're rolling it back, you don't want it to go, you know, the motor will keep running unless something stops it. Okay, so they just had a start, and it went all the way down until the limit switch stopped. Okay, when it came back up, it stopped until the limit switch got. Okay, we had a couple times where the thing was trying to crank itself up because something got stuck underneath the limit switch, and the limit switch wouldn't turn off, so the motor's still trying to run. Snap switch, it's just a regular single pole. It's just a regular switch. So that would be your single pole and double pole, or 3 poles. It's just a snap switch. Turns on and off. Foot switch. Okay, we have them on drill presses, we have them on table saws, or anything device that you want to have control. Okay, so while you're working on it, as long as your foot is on that pressure, on that switch, whatever you're working on is working. Once you take your foot off, that's your device. It's a safety device. In case something happens, you get hit, you get knocked down, it doesn't continue to run because it stops once you relieve pressure off the foot switch. And then a pressure switch is you have a gas line or a vacuum line or something. So it allows vacuum or pressure to turn it on or turn it off. We used to put the on the water. We used them on the water, not a float switch. It was a pressure switch. Why? Because it would sense water, and then once it would hit, it would sense pressure. And well, it was the same thing, kind of. But when the surgeons went in, guess what? When they wash their hands, they can't touch anything. So we had a device that will send your body. So when you touched it, the water would come on. So all you have to do is get up there with their knee, touch it, it come on, and had a device on the water line. Okay, so once they felt that pressure there, to sense something, it would open up the switch and water would run. Once it didn't send it, it would close again. Okay. Two-wire controlled circuits, and this is where I'm going to stop here. I'm going to talk about this before I go into the three-wire. I'm going to talk about two-wire now. So a two-wire controlled circuit, it provides low voltage release, but not low voltage protection. What does that mean? Is, like I was talking about earlier, I turn the switch on, this motor comes on, guess what? Power goes out. Okay, when power comes back on, say that motor, I got a machine, and it's when I walk the machine, I turn the motor on, because it just has, a switch. I walk away, power goes out, I walk away, power comes back on. If I'm not in the machine, what's going to happen? That motor starts running. That piece of equipment would start to work. So that's one thing bad about it. It's great in an area where it wouldn't make a difference if it's on or not. Like say you got a vacuum pump or something, so it's running constantly. We have a few of them that are wired like that for exhaust fans. And that switch is always in the on position. If power goes off, okay, fine, it went off. But when power comes back on, we want that exhaust fan to work because it controlled the fume hood where they had no control down below. Because the fume hood had to run 24/7, so somebody wouldn't walk away. If they were working on an experiment, they want to make sure that they couldn't turn the exhaust off. So that way, in case they left something there, it's still exhausting. So we had them wired before they had control, and we would turn around and rewired them where they had no control. So they were always on. We had control and we had to work on it. But the person operating inside the exhaust, the fume hood, they didn't. So that was for safety reasons that we took them off. But it had a switch. So if power went off, the exhaust fan went off. But when power came back on, that exhaust fan came back on. Why? Because it had to run 24/7. Because you never knew when somebody's going to be in there working. So, and then cannot anticipate when the motor will start. And so unless you're standing at the switch, if power's on and that switch, if you see it's in the on position, guess what? It's working. If you walk away and leave it in the on position, power goes off, guess what? You don't want it to come back on. Don't use these two-wire circuits. When power is lost, control circuit, the contacts will release, stopping the motor. When power returns, the coil is re-energized, starting the motor. Low voltage protection is missing, so there's no way to anticipate when the motor will start. Therefore, extreme caution must be exercised when servicing a two-wire circuit. So when you're working on one of these circuits, you better make sure you turn that breaker off. Lock it out, tag it out, make sure nobody can turn it back on to you. Wherever you have the switch, I'll look for my, wherever you have the switch. I left it at school. My lockout tag, that's at school also. Okay? Put something on that switch so nobody can turn it on. Okay. And if you got to stop starts, put something on it so nobody can turn it back on you. Put a no tag on it. Wherever you can, put a tag on. Wherever there's something you can turn on, put a tag on it. That way they know who's working on it. So nobody turns it back on. Because you're in there working, somebody comes in there, hey, why is this off? Working in an area, I turn some breakers off. Because I couldn't put a lock on the panel. I taped them all off and I put a tag on the inside. Been working. Somebody went over there, opened the panel up because they lost power in the room, pulled the tape off, turned the breaker on. Why? They weren't supposed to have access to this panel. They had access to the panel. Okay, that person could have almost lost his job because he did something he wasn't supposed to do. Okay, so you always have to be, there's some stupid people out there that, hey, why is this off? And don't ask. They just turn it back on because there's no tag. Well, people turn them off even when there is a tag. So you have to protect yourself from injury, shock. Last thing you want to do is have this motor come on while you got your hands in there. All of a sudden you end up like this. Not fun. Okay. So this is a two-wire controlled circuit. Again, there are getting power off. It comes off to one contact, but it's always closed, and this would be here on my overloads, and it's always closed if I want to. Okay, so this one gives me the option, normally open, normally closed. So the normally open is, let's say I got two motors. So when that one turns off, it turns this one on, and that's why it goes to the normally open. I mean normally closed. Okay, so it goes in, normally open, I'm sorry. And then here is my switch. Turn it on and off. Go across. So the elementary two-wire control, wire diagram. These are wiring diagrams. One's an elementary, one's a two-wire. But for the most part, this is still a wiring diagram. So you have a wiring diagram and you have a ladder, which is the schematic. Okay, so the wire. This is a wiring diagram. There's your ladder, and that's a wiring diagram. Your ladder and your wiring diagram. Alright, along with this video, I'm going to send assignment 2, chapter 14, so it'll be some questions like we did with the last video. Hopefully I'll try to do the Zoom. I'll do the Zoom classroom. I'm not going to do it tonight. I'll wait till we get through this one. It'll probably be Thursday night. It'll probably be Thursday night, and I'll do another Zoom meeting. Alright, y'all have a good one.